Hi everyone, it's Mr. Hamilton here. This video is all about exploring the properties of exponential functions. Below the video, there's a link to the handout that you can print off and fill in as we go, just the same handout I'm working through here. We're going to look at the various properties including domain and range, intercepts, and asymptotes. What we're going to do is we're going to look at the tables of values and generate those tables of values for three different functions. The first two you should be very familiar with. An exponential function has an equation of the form f of x equals a times b to the x. Notice it's just b raised to the power of x, not a. Where a and b are constants, b is greater than 0, and b cannot be equal to 1. The base has to be bigger than 0. We'll look at it in a later video. And b cannot be 1 because if b was 1, 1 to any power is still 1. So you just have f of x equals a times 1, which is just a. So the first table of values, to generate those values, we say g of x is equal to x. So the y value, g of x, is just x. So we just copy those values over. So if x is negative 3, then the g of x is negative 3, etc. Just copy those values over to the next column. So then we look at the first differences. Negative 2 minus negative 3 is 1. And we continue that pattern, and all the first differences end up being 1, as we would expect with a linear relation, as we should expect and know that by now. So that's a linear relationship. First differences are constant. We'll come back to that in a minute. The next one is h of x equals x squared. And so you take the x value and you square it. Remember that if it's a negative and it's squared, it becomes positive. And so you can see how I got 9, 4, 1, 0. And then we get to the positive values of x, and we get 1, 4, 9, 16, 24, etc., 25, etc. So then we take the first differences of those. 4 minus 9, that gives us a difference of minus 5. Then we do 1 minus 4, negative 3, 0 minus 1, negative 1, etc. And we find the first differences as shown. Then we do the second differences. Negative 3 minus negative 5 gives us 2, and all of them end up being 2, just as we would expect for a quadratic relationship. So as already noted, the first situation, g of x, is linear because the first differences are all the same. The second situation, h of x, is quadratic because the second differences are all the same. And then we move to the exponential situation. K of x equals 2 to the power of x. So 2 to the power of negative 3 is 1/8. If you didn't know that, let's just look in the corner here of why that's the case. Exponent rules say that a negative exponent needs to be moved to the opposite side of the fraction. So if it's in the numerator, it moves to the denominator. 1 over 2 cubed is 1 over 8. We do the same thing for 2 to the negative 2. It's 1/4. For 2 to the negative 1 is a half, and then etc. Notice anything to the power of 0 is 1. And we continue that pattern. Now we get to things that we're more familiar with, perhaps. 2 to the power of 1 equals 2, 2 to the power of 2 equals 4, 8, 16, and 32. We calculate the first differences. It's a little tricky because you've got fractions, but you take 1/4 and we subtract 1/8 from that, and we get 1/8. Then we continue that pattern, 1/2 minus 1/4, we get a quarter, then we get a half, then we get a 1, then we get 2, 4, 8, 16. You should see a pattern that's emerging here. Now we move to the second differences. A quarter minus 1/8 again, we get an eighth. 1/2 minus a quarter again, we get a quarter. And the same pattern follows again. Now that won't always be the case, but what will always be the case is that if it is exponential, the value that we multiply each y value by to get to the next one will always be the same. In this case, it's 2. We're multiplying those all by 2. And that same thing happens with the first and second differences as well. We multiply all those by 2, and that gives us the next value along the way. So now it says describe the difference pattern for each of the above functions. G of x, the first difference is the same, it's linear. H of x, the second difference is the same, it's quadratic. And then in this third case, we find that the first and second differences are not the same, but the y values and differences all increase by the same factor. In this case, the factor is 2. It won't always be 2, but in this case, it is. Step 3 says to graph g of x, h of x, and k of x. Draw a smooth curve through each set of points. Label each graph with its equation. So I'm going to label those 3 graphs. Pause the video, draw the graphs, and then check back in with me. So what you should get for g of x is you should get a linear relation, those dots that you get from the table of values, and then you join the line of best fit through them like shown. So that's g of x, each equals x. For h of x, you want to set an appropriate scale. And so you see I went up by 4 so that I can fit the 25 y value in. And then I've drawn that as shown. So that's h of x equals x squared, clearly a quadratic. And then for k of x, notice that I need to fit the point 532 in. So I'm going to go up by 5s in this case because that's an appropriate scale to get that last point in. And notice I'm keeping the x values, the scale on the x axis always the same. They're always going up by 1. but I do have to change the y scale on the second and third graph here. So if I continue doing that there, you can see I'm just graphing all those points just from the table of values, starting with the x value, then adding the y value. So going over, then up, and I get a graph that looks like that. So it's getting steeper and steeper as we go along. So that's exactly what the chart below is asking us. It says, complete the chart below. We want to identify the domain and range for each of these functions, and then describe how the y values change as x increases or decreases. So for the linear case, x is a set of all real numbers, y is a set of all real numbers. We know it continues to go up to the right and down to the left. So as x increases, y increases. And then as x decreases, y is also going to decrease. So for the next case, the quadratic case, we can say that x is a set of all real numbers and y is a set of all real numbers such that y is greater than or equal to 0. And the reason for that is because the vertex comes down and touches 0. As x increases to the right of 0, y increases faster and faster. As x decreases left of 0, y increases faster and faster. So it goes up both sides of 0. We should also add the appropriate brackets to make sure we're writing that in the proper notation for domain and range as shown. So now we move to the exponential case. And so what we're going to do here is we see that x is a set of all real numbers again. Y is a set of all real numbers such that y is greater than 0. It's going to come and approach 0, but it's never going to hit 0. It's not equal to 0. It's going to get closer and closer to that line. We call that line an asymptote, but it's never actually going to touch it. So as x increases to the right of 0, y increases faster and faster. And as x decreases left of 0, y decreases slower and slower. So it's not very steep to the left of 0, but it's very, very steep and steeper the further you get to the right of 0. So now we're going to look at three exponential functions. There's the f of x equals 2 to the x as we've seen before, but we're also going to look at when we increase that base. So if we make the base 5, we get that, and if we make the base 10, we get that. It gets steeper and steeper to the right of 0 if we increase that base. That's what we notice here. So let's look at each of these functions, and let's list the domain and range, intercepts, and asymptotes of each of those. So you notice that they all go through the point 0, 1, and you notice that they all never cross that y equals 0 line. They're approaching it, but they never touch it nor cross it. So there's our asymptote, and then there's our intercept, one of our intercepts there, that 0, 1 point. We notice that the 10 to the power of x is the steepest, and 2 to the power of x is the least steep. And so let's go ahead and fill in the chart on the right with that information. So the domain and range of f of x, x is a set of all real numbers, and y is a set of all real numbers such that y is greater than 0. This is exactly what we identified on the previous section, and nothing's changed. It's still the same function. But we notice that's the same for 5 to the x and 10 to the power of x. They have the same domain and range. The intercepts, there's no x-intercept for any of those, but yet as we identified a minute ago, there is a y-intercept at 0, 1, and so we'd say that the y value is 1. There's an intercept at y equals 1. The asymptote is that line y equals 0 in all three of those cases. So the base doesn't change any of those identifying characteristics of an exponential function. So it says, examine the above curves. All of them increase as you move to the right. How do the rates of increase compare? How do the rates of decrease compare as you move to the left? And so let's do that now. As you move to the right of 0, h of x equals 10 to the power of x increases the fastest, but f of x equals 2 to the x increases the slowest. And then as we move to the left, we see that h of x decreases the fastest, but 2 to the power of x decreases the slowest. And so you can kind of see that. I'm trying to label that on the graph for you, that the one that dips down the most is h of x. So step 7 has three different graphs. We still have the y equals 2 to the power of x. Then we also have y equals 1/2 to the power of x. This is g of x is what we're calling it. And then we have y equals 1/10 to the power of x. That's h of x. We're calling that one. And so what we can see here is they all go through the point 0, 1. They all have an asymptote that's the same. And we're going to find that even with the bases that are fractions, we end up having the same properties that we had before. So this hasn't changed. This is still 2 to the power of x. And then the domain and range are the same for these other ones, except they're going down instead of going up. The intercepts are the same. There's no x-intercepts, but there's the y equals 1 intercept at 0, 1. And the asymptotes are still at y equals 0. So then it said, describe how the graphs of g of x and h of s differ from that of f of x. Well, clearly it's going down, but there's more to it than that. It's not only going down, but it's reflected over the y-axis. If you notice 2 of x, 2 to the power of x, compared to 1/2 to the power of x, all those points are just reflected over the y-axis. Well, why is that? Let's have a closer look at these two equations. We have y equals 2 to the power of x, and then we have y equals 1/2 to the power of x. Now, remember our exponent laws. 1/2 to the power of x is the same thing as saying 2 to the power of negative x, because then that would bring it down to the bottom. And so what that means is that the k value is equal to -1. Well, what was a k value of -1? That meant it reflected over the y-axis. And so that's exactly what's happening when you make a base, the fraction, 1 over that same base. This next video gets into more of the equation and how to graph exponential functions, so check that out. Thanks for watching, and if you like this video, please give it a thumbs up and subscribe.